Hello, class. Alright, so we're going to talk about work in thermodynamic processes. So I want to look at an example. Let's say we have a cylinder with a moving piston, a movable piston. And so there's a gas inside the cylinder. Piston can move up and down. And, say the gas expands. It's going to be pushing on this piston, and the gas is going to be doing work on its environment in that case. So, like if we have a mass here, if the gas expands, it's going to be, doing a significant amount of work if we have a large mass here. And similarly, if the mass compresses the gas, then work is going to be done on the gas. And if you remember work, I'm going to write down kind of a simple form for work. Let's just write it like this. Work is F delta X. Now, it's very important to remember that work, force and displacement are both vectors. And so direction can definitely matter significantly. Like if I've got this box, if I'm pushing it across an even surface, pulling it across an even surface, gravity is exerting a downward force, the displacement is perpendicular, gravity is doing zero work on this box. So direction matters. But if we have an example like this where the gas is expanding, it's doing the force and the displacement are going to line up. So we don't have to worry about angles. But work can be either positive or negative because it depends on, if the gas is expanding, it's doing work on the environment. If the gas is being compressed, there's work being done on it. And so we do have to worry about the plus and the minus side. But right now, let's just look at the magnitude of work. Let's say the gas is let's say it's going to expand. And so it's going to push the cylinder upwards. Let's say a distance delta X, then work is just going to be F delta X. Now, pressure is force over area. And so we can write the force as pressure times area. Now, we actually have to be a little bit careful in doing that. And we have to assume that this process is what we call quasi-static. And the reason, what that means, static means nothing is happening. Things are remaining stationary. Or, no changes. And quasi-static means there is a change occurring. I mean, the gas is expanding. That is a change. However, it's doing so fairly slowly. Like if the gas were to expand very rapidly, we could get, it's not going to behave in an ideal fashion anymore. Talk about like the ideal gas law. That would not be the case if we had a very rapid expansion. We can get kind of turbulent air currents inside. And it can even be difficult to define pressure in all cases. If we have turbulence going on. So we assume that every process we consider is going to be quasi-static. It's going to be occurring slow enough that pressure is meaningly defined. So here, we assume that just going from this line to this line. A would be the area of the piston. And if we look at what happened, say the piston started here, and it's going to end up over here. The volume, this quantity A delta X, is equal to the volume that the piston moves through, like the volume that the gas expanded. Yeah, so like this is its initial volume. delta V is going to be the expansion here. That's equal to A delta X. So we can write this, the magnitude of the work would be P delta V. Now that's for some finite process. We have a finite displacement delta X. But what if the pressure is not constant? You know, we can't just plug it in, P delta V. If the pressure is not constant, we'd have to integrate. We have to consider a small change. So we can say that in magnitude, dW is equal to P dV. And then to find the magnitude of the work, we integrate P dV from its initial volume to its final volume. So this gives us the magnitude of the work for any quasi-static process. Now, what about the plus or minus side? And this is really kind of comes down to how we want, like what convention we want to adopt. So I'm going to jump ahead a little bit. Later on, we're going to talk about the first law of thermodynamics. I'm going to write this down over here, and then I'll erase it because we don't really need it yet. First law of thermodynamics, we'll see later, is written this way, where E internal is the internal energy of the gas. And so on the left side, we have the change in internal energy. And Q is heat exchanged. So if heat enters the gas, if we have heat from outside entering the gas, that's going to raise its energy. So if heat is entering the gas, Q is going to be positive. If heat is escaping from the gas, Q is negative. That would decrease the energy. But from this, this convention that we adopted here, where we have Q plus W, some books actually write Q minus W, which is fine too. But the way we define the first law of thermodynamics, W would have to be the work being done on the gas. So, because if you're doing work on the gas, you are increasing its energy. And so, to define work, we want to put a minus sign in front. Like in this case, let's just look at this expansion of the cylinder. In this case, the gas is doing work on its environment, and here delta V is positive. The volume of the gas is increasing, and if it's doing work on its environment, that's causing it to lose energy. And so, you know, we integrate dV, we're going from some initial to some final. Let's say we're increasing in volume, the work should be negative. So let's write that result down here. So with the convention that we adopted, we put a minus sign in front of work. Okay, so yeah, again, this applies to any gas that undergoes a change in volume, in a quasi-static way, where pressure is meaningfully defined. We're going to talk about some specific processes. But before we get into that, I want to look at a very useful way to graphically look at thermodynamic processes. I'm going to move this up a little, kind of overlaps. Okay, so if we look at a gas, assuming we have a nice well-defined ideal gas, we have the ideal gas law, where P is pressure, V is volume, N is the amount of gas present. So if we have a particular gas in mind, like say we have 3 moles of a gas, and that is not changing, we have 3 variables. that can change: pressure, volume, and temperature. And unfortunately, we can't plot all three at the same time on a two-dimensional graph. But it turns out to be very useful to plot what we call PV diagram. Let's say basic SI units, pressure in newtons per meter squared, and the volume in meters cubed. So basically, we're showing a relation between P and V, and what's missing here is temperature. Sometimes we can write that in. We're going to look at an example of a one type of thermodynamic process called isothermal, where the graph is going to look like this, and you can just write the temperature down. Like for this line, we can just say it's 300 Kelvin. So temperature is a factor, but we can't plot it as well in two dimensions. You can try a three-dimensional graph if you like, but I don't want to try that. So anyways, these PV diagrams are very, very useful. And again, if you look at, let's say we just make a dot on a PV diagram, that's telling you the state of the gas, except for the temperature. Just from this, you can read the temperature and volume of the gas. So these aren't like functions of time, where at any given time you get one piece of information. This is like the state of the gas. It gives you the pressure and the volume. So that would be represented by one dot on this graph. Now in a process, let's say we start at A and we end at B in some completely arbitrary way. So we go from A to B, and as you trace along this gas, you start here at some random point. The pressure and volume are constantly changing here, and every dot gives you the pressure and volume at that particular time. And again, there'd be a temperature associated with each dot, but in a sense, we don't really need the temperature, because if we know the pressure and volume, and we're assuming that we know the amount of gas, we can only solve for the temperature if we need it. So we can consider this a complete, for an ideal gas, this graph gives us every dot gives us the complete state of the gas, as long as we know how much gas is present. Okay, so maybe it's best if we consider a particular process. Let's start with the simplest process. Say we have a horizontal line here. We're going from A to B, purely horizontal. And we can see the volume is definitely changing. We start out at this volume, we end up here. This gas is expanding. And the pressure, though, is remaining constant. Whatever this value is at point A, pressure is the same at point B. So let's calculate the work done in this particular process. So we can just write from the definition minus the integral of P dV from, let's call it VA to VB. We're starting at A and we are ending at volume B. Now the pressure in this case is constant. So we can take that out. And then the integral of dV is just delta V. If we integrate that, we have V, we plug in the limits, we have VB minus VA. That's a change in volume. Got the minus sign here. So the work is equal to minus P delta V. Now this process has a name. I'll write that down here. This is called isothermal isobaric. Now, that term iso, that means kind of like the same. I imagine this is Latin or something, the origin of these words. That's used a lot, iso, for same. I don't know what the actual word is, but in physics, if you see that. Now, bar, you might have heard that term like pressure measured in bars, or you've probably heard of a barometer, which measures pressure. So that term bar is related to pressure. So what this means is like same pressure. This is a process occurring at a constant pressure. So kind of knowing the, analyzing the word that itself can actually give you a hint what it means. So I think like barometer, pressure, so constant pressure. Okay, so that's an isobaric process. And here we start at volume A, and we end at volume B. And so the distance between these 2 points, that's the change in volume delta V. And P is this constant pressure here. And so P delta V is the volume, the area underneath this PV diagram. So that magnitude of the work is the area under this graph. Now, that applies to an isobaric process. What if we have a more general process? Where, just some random from A to B. So we can draw these vertical lines. And again, the magnitude of the work is the integral of P dV starting from, V initial to V final. And we know that, the integral gives the area under the curve. So in general, for a PV diagram, we can interpret the work as the area underneath this curve. So that applies in general. Now, when we're going from, say, A to B, we're basically tracing this curve from left to right. And so, by our convention, that makes the work negative. So, the gas is expanding, and it is doing negative work. Or, it's doing work, but the work, we're talking about the work being done on the gas. So if the gas is doing work on its environment, we can say the environment is doing negative work on the gas. When the gas expands, it's doing work, it's expending energy, so its energy is going down, and the energy is going into the environment in whatever form. Like you could have a piston, you could lift up a mass. So that converts it from the internal energy of the gas into the potential energy of whatever that mass is. Okay, and now here going from left to right, the work is negative. If we reverse the direction, if we have it going from right to left, then the volume is decreasing and there's work being done on the gas. So for a right to left process, work is a positive value. So here work is negative, here work is positive. And there's actually a really important type that we're going to come across later, an important type of process that we can draw on a PV diagram. I'm just going to draw maybe a not very realistic example. Let's say we start here and finish it. This is a cyclic process. And so we start at some point. Here our volume is increasing. Here the pressure drops. Here the volume is decreasing. And then we bring back the pressure. Point is, we end up back at the same state in which we started. So it's called a cyclic process. We could do it again and keep repeating this. And if we look at, I guess we're going to look at our next example. This is called isovolumetric. So again, iso, just think that means same volume. So like from here to here, this is isobaric. And this process here is can barely fit on there, but isovolumetric. And if we say the work is the area under the curve, if we have a vertical line, the area underneath is 0. And so the work is 0. If you try to do this integral as well, dv is 0. It's not changing at all. So yeah, the work for an isovolumetric process is 0. So let's look at, let's label these differently. Let's say A, B, C, and D. And let's look at the work as we go through this cycle. So first off, work from A to B. We're going from left to right. That would make it negative. Sorry, 1 second.